The output of finite state machines can be categorized as either Mealy outputs or Moore outputs. And these are the names of the scientists that actually studied these types of outputs in the 50s. Please note that in the next discussion, Mealy outputs and Moore outputs are not exclusive. Sometimes some of the machines or some of the finite state machines will have both of them. But for the sake of simplicity, we're just going to discuss them one at a time. All right, so we know by now that a finite state machine is just a general synchronous system that contains flip-flops, or what we call a state register for now. A bunch of flip-flops, we call them a register. So because we usually have more than one flip-flop, let's say 2 or 3 flip-flops, so we have a register or a bunch of flip-flops, we usually call it state register. So why do we call it state register? Because it actually stores the state of the system, which state we're in. Are we in S0, S1, S2, S3? But anyway, we have seen this diagram before, and what I mentioned is we have a state register in here, and usually you figure out the next value of the state using some combinational logic, and this combinational logic is connected to, sometimes connected to an external signal, not all the time, but you have the option of doing that, and some output logic, which is also combinational logic that detects what the output is. Sometimes this output logic is just exactly the value within the state register, for example, what we've seen in counters. So what's the difference between a Mealy output and a Moore output? Well, it is actually this particular red line in here. So what does it mean? Well, a Moore machine, okay, a Moore machine tells me that the outputs in here only depends on the current state, which means if I want to have a Moore machine, I shouldn't have this line in here at all. So a Moore machine is a machine that depends that the output logic is only a function of the current state. It's not a function of the input. So this current external or the external input cannot appear in the output at all. You can have, again, this output logic just is based on the state register values, and that's it. But anyway, so you shouldn't have any input from the outside world. However, a Mealy machine, on the other hand, okay, a Mealy machine here, you will have this particular line in here appearing. So if you see the external output or the external input coming to not only the next state logic, but also to Mealy output or to the output directly, bypassing the state register and affecting the output directly, the outputs will be Mealy output. So what does this mean, or how does it affect it? Well, if you have a Mealy circuit, that means the output is not necessarily synchronous, and the output can change whenever the input here changes. It doesn't only depend on the clock, and that's actually a big deal. So let's see this using the implementation of the sequence, the 0, 1, 1 sequence detectors that we've seen before. So some of them are Mealy, some of them are Moore. Usually I take a look at that and I see, okay, here's my output. Let's take a look at this. Here's the output. This output only depends on B and A. It depends on the current state. So technically it doesn't depend on X. So this is what we call a Moore machine, or a Moore output for that matter. How about this guy in here? Well, this guy has the X, and this actually affects it. I don't even have to look at anywhere else. This is just a Mealy machine. Okay, how about this one in here? Well, this one here depends on this one, this flip-flop, and this flip-flop, and it doesn't appear that X actually appears in the output directly. So I don't have that red line. So this happened to be a Moore machine. So all of them technically perform the same functionality of detecting a sequence of 0 followed by 1 followed by 1. But sometimes, or there is a difference between a Moore machine and a Mealy machine. So I went ahead to Verilog and I wrote some code to describe these circuits. So let me show you. All right, so here in Vivado, you can see the I've written a few modules. So the first one I'm showing you is actually this one here, which is a Mealy output. I called it Mealy 011 detector. And if you can take a look at it, it's really a straightforward implementation like what we've seen in counters and any synchronous systems we've coded before. It actually has 3 parts. The part that actually has the state register in here, or all the sequential circuits where the clock is. These are basically the flip-flops in here. Okay, and then you have the next state logic, and really what the next state logic is, whatever is the state, actually it's the state equations, and I got them from the state equations. So I just called, just for the reference, I called, because I always deal with A followed by B this way. So what you will see is this is index 1, and this is index 0, this is index 1, this is index 0, this is index 1, followed by, well, this is index 2 followed by 1 followed by 0 in this particular case, okay? And that's what you will see in here. So you'll see that the state register, or I'm defining something called state register, and it's a couple bits. And you can follow the table or the equations in here. They're exactly as the state equations. And then of course the output in here, what defines it as a Mealy output is this little X in here. So X is actually an external input. So X is appearing directly in the output. All right. So that's for this particular circuit. How about this one here? Let's take a look at the code for this guy. It's pretty much the same. I have the same thing in here with the reset and the state register. All I'm doing is the next state logic is a little bit different. It's based on the state equation for this particular guy in here. And now if you take a look at the output X does not appear in the output at all. And that's why we call it a more machine, or a more output, not a more machine. Because if you define it as a more machine or a Mealy machine, that means there's no other outputs. So, well, in this case, there is no other output, but you might have another, for example, Y2 that actually depends on the X sometimes. If you want to, you can have both outputs for a single finite state machines. And then the last one in here, it's actually a little bit more implementation here. I have 0, 1, 2, or a little bit more flip-flops. So that's why the state register is 3 bits. And you can see implementation-wise, it seems to be, if I use a little bit more flip-flops, I have less complicated next state logic or output logic sometimes. Well, next state logic seems to be a little bit less complicated in here versus here and versus here. All right, and you can follow the diagram as well. Again, it's a more machine because X does not appear directly in Y and shouldn't affect it. So how does this affect me, or what is really the difference between a more machine and a Mealy machine? Well, as we mentioned briefly, if X appears in the output directly, the output changes regardless of the clock. So here's a single test bench that I wrote. So let me just show you the code very briefly. So in this test bench, what I did is instead of writing a test bench for each one of them, I combined them all. So you'll see I wrote a module and instantiated a unit under test, another unit under test, and another unit under test. They all have the same clock, reset, and X input, but they have different outputs. And I'm showing you the different outputs in here. So for example, Y more, Y Mealy, Y more 3 flip-flop, which is this one here for 3 flip-flops. So let's see the distinctions in here. So technically, since it's looking for a 0 followed by 1 followed by 1, I should be looking at the same outputs. And as it turns out that no, only the more outputs, which are this one and this one, are the same. This here is a more and the more, but the Mealy is a little bit different. So let's see it. All right, so it is looking for the sequence 0 followed by 1 at the clock cycle. So here's the active edge of the clock in here. I'm resetting everything, so that's a 0. And then I'm following it by a 1 and following by a 0. That's not the sequence I'm looking for. But this one here is a 0 followed by, let me just see, I'm looking for a 0 followed by a 1 followed by 1. So wait, what happens in here? It's not on the other more outputs, but the Mealy output at 1. So let's actually discuss it for a short period of time. So it's, or let's discuss it. So that here is the input X, okay? And the input X happened to be a 1. Well, that's fine. I don't care about it. I'm looking for a 0 followed by a 1, and it's still 1 right after that clock cycle. So it's a 0, 1, and it's still a 1 after that clock cycle, even though here, and you can see it, it's actually happening, or it's actually outputting a 1, detecting that I've detected a 0 followed by 1 that lasted a little bit longer than that next clock cycle. And when did it end? It's actually ended at the negative edge of the clock. And if you take a look at all the codes that I've written, they're all the active edge is actually the positive edge. And that's why you will see that this particular output in here lasted for less than a clock cycle. So let's do the same exact analysis in here. You will see that this X in here, it's actually the active edge of the clock happened to be here. That's a 0 followed by a 1. And then it stayed at 1 afterwards. So what you can see is the Mealy output in here, it's at 1. However, the more output is usually delayed by 1 clock cycle. So that's the main difference and main distinction between a Mealy and a more machine. So in a more machine, the ones in here that doesn't depend, that the output depends only on the current state. You will see that an active edge of the clock is 0, another active edge of the clock is 1, and it has to wait for the next active edge of the clock. And that next active edge of the clock is 1 when the output here is 1. What happens in the Mealy? The Mealy usually respond a little bit faster. So I had a 0 followed by a 1 in here, and it stayed at 1. And as long as that X output is actually at 1, that's it. It stays at 1. And that's what happens in here. But anyway, and well, it stays at 1, of course, because it's looking for 0 followed by 1 followed by 1. And next active edge of the clock, if it stays at 1, that became 1, 1, 1. So this is here, it's an active edge of the clock. This is a 1, this is a 1 followed by a 1. So it's nothing I'm looking for, so it went back to 0. But take a look at like really an overview of what's happening in here. what you will see is the more output is delayed, so it's a little bit after. So after the third clock cycle comes in, it will be asserted. And it lasts for the whole clock cycle. So from here to here is actually 10 nanoseconds, from 85 all the way to 95. However, the Mealy machine, whenever it's asserted, it's not guaranteed to be asserted for a whole clock cycle. So it got asserted here for a short period of time, and then here for a whole clock cycle. And you will see that it's not synchronized with the clock. It can actually be deactivated with the negative edge of the clock.